Hi there, my name is Rusty Yates, and this is my capstone presentation. It's called the REEsource Geospatial Data Pipeline Prototype, and go through a few slides talking a little bit about it. So, the pipeline was developed to help identify potential deposits of critical minerals and rare earth elements. Those are required for modern technologies in the U.S. economy and for our national defense. This prototype was developed to aid the rapid discovery of economically recoverable deposits, potential untapped, mineable near-surface deposits based on USGS survey data across the United States. This data pipeline and those like it can help reduce critical mineral exploration costs while verifying the scale of existing deposits, contributing to national consensus on the most valuable near-term recoverable deposits. It's a digital-first exploration approach. Prototype uses an open source machine learning pipeline, and it analyzes 4 dimensions of geospatial data. Proxy data is compiled over a region via potassium, thorium, and uranium radiation and magnetic structural indicators. This is typically collected via onboard instruments in helicopters or other airborne aircraft. So pipeline utilizes ML clustering algorithms to help scientists unpack the most notable areas of interest across more dimensions than standard maps are capable of visualizing. So core technology for the machine learning pipeline is the HDB scan algorithm. It stands for the hierarchical density-based spatial clustering of applications with noise. It's well suited for non-spherical, noisy, multidimensional geospatial data. The application file cluster.py, which is available in the GitHub repository, enables optimized runs of this algorithm for a given regional data set with the 4 dimensions used in this prototype. It can be used on multiple data sets and not just the one survey that the prototype was designed around. So in order to determine which anomalies are of interest and valuable, the algorithm was tuned to only return the most dense and distinct clusters from each pipeline run. That is the top DBCV score, which stands for density-based clustering validation, was returned from each pipeline run. The highest DBCV score achieved for the Colorado Mineral Belt mid-block region was 0.9866, which indicated a very dense and distinct cluster across all 4 dimensions. For a single dimension uranium, we received a z-score of 37.89 and statistical confidence of near 0, indicating a very strong anomaly in that region. However, this pipeline was built to analyze 4 dimensions of data across a very large area, not just a single dimension in a single survey. So we tended to use the DBCV values instead of calculating statistical confidence for a single variable. Okay. The model independently discovered a very strong 4D anomaly in the Powderhorn region of the Gunnison in Colorado. It was located around the historical Iron Hill mine. Until the model ran and produced this high DBCV value and the resultant polygon, I had no knowledge of this mine, region, or its history. Upon further research, there were several articles in local newspapers in the Gunnison area mentioning increased interest from several organizations for the potential recoverable REE deposits in the area. Map on the right kind of shows where we're looking if you're familiar with Colorado at all. That's in the Gunnison National Forest. It's just south of Blue Mesa Reservoir near Powderhorn and the Iron Hill mine. Okay, enterprise infrastructure, we're looking at the dashboard. This is the app. The prototype was developed using Google Cloud Platform, or GCP, and it's able to take in survey data from any state in the nation, returning similar identified anomalies with the highest DBCV scores as an end-to-end pipeline. And it puts the resulting areas of interest into an overlay on a map. in an ephemeral application dashboard. This is using Streamlit for the front end. And we see the HDBC scan, active target zones, and some more stuff about how the application was set up. App is available at reesource.streamlit.app, and we'll spin up a new node upon request, showing the most recent data. Code is made available publicly under the MIT license with full version transparency over the duration of the development process from initial commit to the current state. Here are some select references and documentation pertaining to this presentation and the excerpt of the whole project that we're trying to summarize. Appendix, we're going to do a brief pipeline walkthrough. I took screenshots when ingesting a complementary data set for the Northeast region. It ended up not working, but it gives a good example of how the data can be ingested. And further iterations and development improvements could automate this ingestion approach for different surveys, assuming that the USGS contractors made the data available in GeoTIFF format and not necessarily shape files. So this is Sciencebase, where the survey data can be found. Again, this is for the Northeast block. The mid block is what the app currently shows. But if you look down at the bottom, there's child items. It shows magnetic and radiometric data. The TIFF files for uranium, thorium, potassium, and reduced dipole magnetism were uploaded. You see the downloads folder from USGS Sciencebase. They have an API that we could probably use, but they need to prove that you're not a robot when you download these giant files. So I just downloaded them locally and then uploaded them to Google Cloud Storage into a bucket called REEsource Data Raw. It's available in US Central 1 data center. We see the files were made available there. They're somewhat smaller in size than the mid-block raw TIFFs. This is how you upload files into Google Cloud. This is part of the config.py file in the application. It's where we're specifying the different file paths. Note the bucket URL, GS resource data raw, that's the collection, or the bucket name, I should say, and then the TIFF files. We set a lot of the parameters for the application in config.py. All right, next up, we're looking at the pipeline runner, which is the main orchestration hub for the entire pipeline. It's the one thing that the different images, when we deployed it to the cloud, this is what kicks it all off. It connects the different config, ingest, cluster, vectorized database files in SRC folder in the application. But this is the orchestrator file. So it's where everything begins, and how it collects all the data and makes the resultant polygons available. Okay, we're looking at the artifact registry in Google Cloud Platform. It shows a Docker image for the REEsource project. This is where we store the definitions basically for the operating system that we spin up every time we do a new pipeline run. Below, we've got a Cloud Shell window open. So if you go into Google Cloud Platform, you can click Open a Shell. It'll have you authenticate and authorize who you are. You have to have the right IAM permissions to do some of this stuff. So it's beyond the scope of this project, but we see the command line bash terminal where we're pulling the most recent Git repository from GitHub, or we're cloning it. Next up, it's cloning into the project. We see that it completed successfully, and then we're changing scope for the terminal into the project, and that's where we build the cloud run definition. So once we start building the Cloud Run object, it takes a while. It brings in all the dependent modules that Python requires in order to run the pipeline. They're all listed here. Installing collected packages is highlighted at the bottom. Takes a few minutes. At the end, you should see something that says success. And in this example, it took about 3 minutes to run. So we've got images here that say Google Cloud Run jobs, create a new job. So we were creating the image before. This is actually creating a job. And we're saying we're going to set the memory to 32 gigabytes, 8 CPU cores, where we're running it in the name of the pipeline, and the latest tag. So now we're going to execute it, and then it says provisioning resources, provisioned containers, done. And then we see in Google Cloud Run where the job is available, and that circle there indicates that it's running. Okay, we can go into the logs for different jobs, and this will show us, it'll basically give us the console outputs from the Python application. We have these different info records. So it says loading raster, loading raster, loading raster, starting HDB scan, autonomous auto tuning phase. It goes through 3 iterations with different cluster sizes and epsilons, and it picks the highest DBCV score result and puts it into Firestore. This is the logs overview, and it shows that it terminated because it hit a maximum default timeout of 7,200 seconds. So running the pipeline takes some time each time, and this could be scaled up if we had additional resources like horizontal, more than one node running the pipeline, or by vertical scaling, say we improve it to a terabyte of RAM or something like that. But we hit a timeout, so we went back and we made an update to set the task timeout to 14,400 seconds, so just doubled it. We pulled the new definition, then we ran the job again, came through, and this is where we see what it output. And again, this is for the Northeast region, which never made it into the final app. It ended up producing about 200,000 enriched target zones. So I'd have to go back in and do a little more tuning. What actually was happening in this case was the contractors for this survey region produced their actual data in CSV or shapefiles instead of the .tiffs. The .tiffs were just a scaled down red, green, blue value, which is what it was showing here. So if you're super familiar with geospatial files, you'd be able to open it up and kind of see a little bit more what was going into the data there. But in this case, we didn't end up pushing 210,000 target zones to Firestore for the Northeast region. Definitely room to improve, and shows the challenge that I encountered while developing this pipeline. Okay, so here we've got the Streamlit app, the 4D composite detection model. It's also showing the highest DBCV score that we ended up producing. It's in the Powderhorn area over the Iron Hill mine. We have the thorium overlay, so that pinkish purple with the yellow, that's one dimension, and that's thorium levels in the area. The polygons are the 4-dimensional identified clusters, and that would be across potassium, thorium, uranium, and magnetism. So we're just showing one active raster overlay. If we were to put all 4 of those together, they put all 3 of them together into a ternary map, and it makes some interesting visuals, but you can only really put it into 3 colors, so red, green, blue, to indicate what the pixel should show. This pipeline was analyzing 4 dimensions, and just output the regions via polygons as an overlay. So it's analyzing more dimensions than we might normally be able to do. Okay, and this is available anytime. If you go to that app, it might say wake this app up. because it's ephemeral, it's not always running. You just click that and it'll take 30 or 60 seconds to spin up. Okay. Billing for all of the development and deployment cycles. Most of the development and deployment was done in June of 2026. We see 1, 2, and 3 development cycles that cost the most. The first was Gemini API and Vertex AI at the beginning of June. The second approach that I developed used the compute engine, and that was the 8th through the 12th of June when most of those runs and costs were incurred. And then the final approach was using Google Cloud Run along with the artifact registry to create jobs to run the pipeline independently. So we're not spinning up a compute node for 5 days. We're just spinning up a job for however long the pipeline takes to run, which can be a couple of hours. So the total cost was around $10 for all of the development and deployment for this project in Google Cloud. Again, additional resources and time we could put into this and apply it across all of the USGS Emory survey data sets. It could really add some interesting insights into the data being collected for that program today. All right, finally, this is where the code, version controlled code is housed. It's at GitHub and the REEsource project. You see the link at the top there. If you have any questions, please reach out to me here. You can reach out to me on GitHub or through Colorado State University Global. Really appreciate your time, and thank you for letting me do some data exploration and pipeline development. It was definitely challenging for me, got me out of my comfort zone, but it also opened up how I think about different data sets and how we can use them to better our world. Thank you very much.